Let's find the volume bounded by x squared plus y squared plus z squared equals 80 and z equals 1/2 the quantity x squared plus y squared. Let's first look at sketching the graph and identifying the region that is bounded by both of those. The first graph here, x squared plus y squared plus z squared equals 80, that's a sphere. It's centered at the origin, and the radius of that sphere is the square root of 80. And z equals 1/2 of the quantity x squared plus y squared, that's a paraboloid. And the vertex of that paraboloid is at the origin. And let's go ahead and sketch this in 3D. And the equation of the sphere, x squared plus y squared plus z squared equals 80, we know that's centered at the origin and the radius is square root of 80. Let's graph that. And the paraboloid, the vertex is at the origin, and the traces are parabolas in the xy and xz planes. I'm sorry, xz and yz planes. So imagine you have a parabola that opens up. That paraboloid. We want to find the volume that's inside of the sphere and inside of the paraboloid. So it's going to work out that the region here is the region inside of the sphere and inside of the paraboloid. Now when you're setting up a triple integral for volume, the volume is equal to a triple integral, and then we use the letter Q there to denote the solid region, and then we determine the bounds of integration based on the solid region, dV. Now dV itself can be, in terms of rectangular coordinates, it could be dz, that's like your change in z from the bottom to the top, dy, your change in y from the left to the right y, and then your change in x from the smallest x to the largest x. So when we determine the bounds of integration, we want to look at the inside bounds for z. Would be like from the bottom z to the top z. And this is our z-axis, so we want to look at the bottom z to the top z. And then when we look at our bounds for dy and dx, we need to project this region onto the xy plane. When you project this onto the xy plane, you're kind of, what the projection ends up being this circle in the xy plane. And you can shade that projection onto the xy plane, and then we draw that projection in 2 dimensions. That 2-dimensional graph that corresponds, and ends up being a circle, and we want to find the bounds for dy and dx based on that circle. So in order to find out where the size of this circle, we need to determine where the sphere intersects the parabola, the paraboloid. Where does the sphere intersect the parabola? In this portion right here, where the z on the sphere is equal to the z on the paraboloid. And if you solve the equation for z on the sphere, the z is equal to, you're going to subtract x squared and y squared and then take the square root. That is equal to 80 minus x squared minus y squared, the square root of that. And the z on the paraboloid of 1/2 x squared, the quantity of x squared plus y squared. We want to find out where the sphere intersects with the paraboloid, so we're going to set the z on the sphere equal to the z on the paraboloid, because where they intersect, the z's are the same height. Okay, so I have the equation of the sphere, z equals the square root of 80 minus x squared minus y squared, and the equation of the paraboloid. We're going to set the z's to be equal. When we do that, we get the square root of 80 minus x squared minus y squared is equal to, again, the z on the sphere is equal to the z on the paraboloid, equals 1/2 of the quantity x squared plus y squared. And we want to solve this. We can do this a couple ways. One thing we can do is by substitution that will simplify this equation a little bit. And recall that in converting to polar, there's a conversion equation for x squared plus y squared. We know that that is equal to r squared. So we can write this equation as the square root of 80 minus that quantity of x squared plus y squared. That we can write that as 80 minus r squared. And this we can write as 1/2 of r squared. So that way we're trying to solve this equation where we are looking for just r by itself, a single variable. We can do that next step then by squaring both sides of this equation to get rid of that radical. And when we do that, we get 80 minus r squared equals, we're going to square 1/2, which is a fourth, square r squared to get r to the fourth. Okay, now we have this equation. We can solve this polynomial equation by factoring or even by using the quadratic formula. If I move the, if I add, subtract 80 from both sides and add r squared to both sides, add r squared and subtract 80, we can write this as a polynomial equation set equal to 0. So 0 is equal to 1/4 of r to the fourth plus r squared minus 80. And we want to solve this for r. This can be solved by factoring or even by using the quadratic formula. If you let a equal 1/4 and b equal 1 and c is equal to -80 and use the quadratic formula, you can find that when you solve this, you actually get r squared is equal to r squared is equal to 16, or r squared is equal to -20, or you can even factor this polynomial. Now, it doesn't make sense that r squared could equal a negative number. We call that an extraneous solution, so we can eliminate that as an option. But we do get this r squared is equal to 16. And when we go back and make that substitution, we can say x squared plus y squared is equal to 16. And that is an equation for a circle, and the radius of that circle is equal to 4. Now we want to look back at the original drawing where we looked at in between, find the volume in between, and we wanted to project this intersection onto the xy plane. So now we get that this equation here of this circle, this projection in the xy plane, the equation there is x squared plus y squared is equal to 16. So that's the equation of a circle, and the radius of that circle is equal to 4. So what this is going to help us do is determine the bounds of integration for y and x. Okay, so what we have here is we know that we're looking at first the bounds for z, and the bottom z, this is going to be your lower bound for z. Lower bound for z is equal to 1/2 of x squared plus y squared, and your upper bound for z is the equation of the sphere, but you solve that for z. So that's going to be used when we determine our inside bounds for the iterated integral. Now let's look at our bounds for y and our bounds for x. We've got to look at this base region here, and we can draw rectangles, we can draw vertical rectangles, or even horizontal rectangles, and you can solve it in that way. But in order to find the bounds in terms of y and z, we want to find the equation for the bottom y equals to the top y equals. And since our equation of intersection is x squared plus y squared is equal to 16, if you solve this for y, this bottom y is equal to let's go with this. The bottom y, if you solve that equation for y, would be the square root of 16 minus x squared. The bottom of that is going to be the negative part. And the upper portion here, upper portion there, again, if you solve that for y, it's going to be the positive square root of x squared minus, I'm sorry, 16 minus x squared. So the upper bound is the square root of 16 minus x squared. This one is going to be the negative one for the lower bound, and this one's going to be the upper bound. In fact, actually, if we leave making this column here for the upper bounds and the lower bounds, the upper bound for y would be the positive square root of 16, and the lower bound for y would be the negative square root of 16 minus x squared. And then if we wanted to find the bounds for x, your left x, your lower bound for x, since the radius is 4, that left x is going to be negative 4, and that right x is going to be positive 4. So you can use these as your bounds of integration. So our triple integral can be written as follows for the volume, where the order of the differentials is going to be dz, dy, dx. Your lower bound for z is the 1/2 the quantity x squared plus y squared. Your upper bound for z is the sphere, and we solve that for z to get the square root of 80 minus x squared minus y squared. And then our bounds for y, your y lower bound is that negative square root of 16 minus x squared. Oops. And the upper bound for y is your positive 16 minus x squared. And then your bounds for x would be from negative 4 to positive 4. So this is setting up the iterated integral that gives you the volume. Now you can see this ends up being quite tedious here. What you can do as an alternative is, instead of using these vertical rectangles or horizontal rectangles, you can use polar conversions. So now let's look at writing this triple iterated integral using a polar conversion. So instead of that vertical rectangle to determine the bounds, we can slice this like a pie, or even like using concentric circles to determine our bounds for r and our bounds for theta. The bounds for r, in this case, the smallest radius would be 0 to the largest radius of 4. So your bounds for r go from 0 to 4. And your bounds for theta would be the smallest angle 0 to the largest angle of 2 pi. So those are your lower and upper bounds for r and theta. Now, remember the conversion equations. We can replace dy dx, that is our differential area, is equal to dy dx. And when we convert it to polar, we can write it as r times dr times d theta, or even write it as r times d theta times dr. So let's look at what happens when we convert this to polar. We can write this as the iterated integral of dz times dy dx, where we replace that dy dx with r d theta dr, or r dr d theta. In fact, I'm going to replace that with the r, bring the r out in front, and that d theta dr. So now our bounds for z in terms of polar coordinates, we can use a conversion equation. The lower bound would be half of the quantity x squared plus y squared, and that's going to be 1/2 of r squared. That's your lower bound for z in terms of r and theta. And then your upper bound for z would be 80 minus r squared. And then your bounds for theta would go from 0 to 2 pi, and your bounds for r would go from 0 to 4. So you can see in this example, if we use dz dy dx, the bounds end up being quite complicated. You can attempt to work that out, but in this case, when you convert it to polar, you end up with simpler integrals. In fact, the outside ones are constant. So take the time to evaluate this one, evaluating the inside first, and then continue on And when you work this out, you get that the volume of that solid region is approximately 225.2 cubic units.